Good morning, everyone. Today we will continue section 4, work, and then we will start the last section, average value of a function in the section 5. Now let's review the work part we did last time, okay? So according to Newton's law, we know that the force equals ma. M is the mass, a is the acceleration, and if the a is the acceleration, the a acceleration is the constant, then the force is the constant. Then the work done can be evaluated in this way, right? The force times the distance the object moved. In the case f is a constant, right? And if and we did some simple examples, and be careful of the unit feet pound. 1 feet-pound is 1.36 joule. Okay, feet-pound is also the measurement of the work in the United States. And we deal with the situation when the force is a variable, is a function, right? When the force is a function fx, then x denotes the position of the object. So here the force is a variable, and we are interested in the work required, right? In the work required. So here we establish the framework as we did for the integrals, right? For the integrals. And finally we defined that the work required when the object moves from A to B using the force Fx, that will be actually the integral, the definite integral from A to B. The integrand is the function, the force Fx dx, right? So here it will be easier if you use the definite integral formula to work out the work, but we should figure out the force, right? The force is Fx. And of course, the force is not easy to figure out in this section we are going to talk about. And let's still talk about the Hooke's law, the physics part, okay? The physics part. Hooke's law, maybe some of you might heard before in your physics class or not. Okay, let's just study this part. So here we have a spring, okay? We have a spring, and this is the scenario, okay? This is the scenario. So the spring connected to an object, okay? Object, and now this spring is in a natural length, and the surface is assumed as the frictionless surface. So this is called the natural position of the spring. If we check this part, okay, if we check the spring is in the natural length, of course the spring has some length, right? Has some length. If it's in the natural length, do we have any force applied on this object, or do we push or pull this object if the spring is in the natural length? Of course it's not, right? Everyone understand? When the spring is in the natural length, there is no force either pull or push the object. And what is part B? So here we call this position the position when there is no force from the spring applied on the object. The position is 0. Okay, the position is 0. Measure x in meter. We should convert the x. We should convert the x in meter, because we know 1 Newton meter equals 1 joule. We should keep the unit in a standard way. Okay, we should convert. If it's not meters, we should convert into meter. Yes, a good question. Now we mark this position is 0 when the spring is in the natural length. Then we can pull the object, right? We can pull the object from 0 to x, So right now when one person is pull the object, then the spring stretched, right? The spring stretched. So the force for the spring given to the applied on the object will be kx, okay, will be kx. Here, what does this x mean? This x is the object moves x from the natural length, okay, from the zero position to x. That means you can also understand the spring stretched x unit, okay, x unit. We don't care it is either measured in centimeters or meters. Finally, we just convert the unit into meters. There is no worry about the unit, okay? So the spring stretched, the spring has been stretched for x unit. Then the force from the spring which applied on the object will be kx, okay, will be kx. And again, we should be clear about what is x. This is the unit, the x stretched, but the spring the spring does have their own length, right? So we need to be clear. Hooke's law states that the force required to maintain a spring stretched x unit beyond its natural length. Okay, it's this. What is this x? This is the x unit beyond its natural length, and then the force should be proportional to the x unit, okay, should be x unit. This k is the constant, okay, this k is the constant, positive constant, and we usually call it spring constant, okay, that is physics course teach, okay, the spring constant. So of course the Hooke's law will hold provided that x is not too large. X is not too large. For example, if you put the x unit in very large, then the spring will break, right? The spring is break if it's beyond its reliability of the spring, then it will break. That's why we said x is not too large when you either stretch out or shrink, okay, either stretch out or shrink. The shrink, when you shrink, it's also the same thing, okay, it's also the same. Hooke's law also applies, okay, not only for the spring stretched. And if you have some basic knowledge of the physics, the spring stretch or shrink is symmetric, right? If it's stretched x unit, then the force is kx. Or if the spring shrink x unit, the force will also be kx. It's the same, right? It's the same. Just be careful. This x unit is beyond its natural length, and we do have the length for the spring in the natural state, okay, in the natural state. And by the way, if this spring applied, for example here, what is the work required for the object moved from 0 to x? So here, of course, the according to the Hooke's law, the force is a function about x, right? Is a function about x. So let me write here, okay? Let me write here for the part B. So let's think about the Hooke's law after we explain the force. We understand the force is a variable, so we need to use a definite integral. So work required to stretch the spring by x unit. What does this x unit mean? Beyond its natural length from 0 position. What is 0 position? 0 position, which means the spring is in the natural state, right? So from 0 to x, right? from 0 to x, fx, my fx is kx dx, right? That is the work required to stretch the spring by x unit beyond its natural length. Because why we mark here as 0? Because at this station, at this position 0, there is no force. There is no force for the spring, right? There is no force applied because it's in the natural length. Now let's check the examples. Okay, let's check the examples to apply about the spring with the Hooke's law. A force of 40 newtons is required to hold a spring that has been stretched from its natural length of 10 centimeters to a length of 15 centimeters. How much work is done in stretching the spring from 15 meters to 18 centimeters? So let me explain the length. Okay, it's in centimeter, but it doesn't matter. We can convert it into meters. What is my zero? What is my zero now? And this zero, we do have the length for the zero, right? Because we know the natural length of the spring. So that is the natural length. Okay, this is the zero position. This is the uh, this is the zero position, and we call this whole length is 10 centimeters. Okay, 10 centimeters. So this is part A. Part B. So what is the force? 40 Newton is required to stretch the spring from 10 centimeters to 15 centimeters. In this way, right? In this way. So now it's 15 centimeters. So at this moment, the force is 40, right? Force is 40. So what is this x unit? So we can write in this way, okay? The natural length, let me mark those in a clear way. The natural length, I'm going to use the meters. The natural length, I will call it x0, okay? x0 is natural length, which is 0.1 meters, okay? 0.1 meters. Then unit, okay? Unit beyond its natural length. From say 10 centimeters to a length of 15 centimeters. You stretch the spring from its natural length to 15 centimeters. So unit beyond the natural length. I can mark this position. The second position is x1 equals 15 centimeters, right? Then the unit beyond the natural length will be, let me write it in this way. So my x1, I can call the second position is 0.5 meters. Okay, that is the second position. Natural length, the zero position, right? This is zero position. And then x1, this is 15 meters. So the unit beyond the natural length will be x1 minus x0. It's easy, right? It's easy. It will be 0.05 meters. So at this moment, what is the force? Because here the spring constant has not been work out, right? We need to work out the spring constant, because in the former, you should be clear about fx dx, and for the spring, according to the Hooke's law, the fx will equals kx, right? Kx. So we need to figure out the spring constant k, right? Where according to the Hooke's law, for the spring, for the ideal case of the spring, which is placed on the frictionless surface, right? Then at this moment, a force of 40 Newton is required, right? A 40 Newton is required to stretch the spring by 0.05 meters. So at this moment, okay, at this moment, my force, okay, my force will be 40, okay. We can write it in this way. It's not a function again, it's just a fixed value. So 40 newtons, okay, 40 newtons equals, that is the force, equals the spring constant. What is this x? So actually we can, let me just call the unit, beyond the natural length as delta x. So that will be k times my unit beyond the natural length, 0.05. Use the standard measurement, meters. So what is my k? It's pretty easy. My k is 800, right? My k is 800. So we work out the spring constant, okay? Spring constant. But let's read it carefully, okay? Yeah, it's easy to get the k. How much work is done in stretching the spring from 15 centimeters to 18 centimeters? So be careful, okay? Be careful. It's easy to make a mistake here, to write your lower and upper limit. So we know it's easy to write kx, k is 800, kx dx. But what is your lower and upper limit? 0.15 to 0.18? Is that right? Be careful about your lower and upper limit. Is it 0.15 to 0.18? The lower and upper limit are wrong, okay? The lower and upper limit are wrong. Here, you stretch the spring from 15 centimeters to 18 centimeters. As I said again, the spring has its natural length, right? The spring has its natural length. Make sense? So here, you should remove the natural length. My a should be the, you move from, and it's not zero, right? It's not zero. We're starting from 15 centimeters, and at this moment there is a force applied. Of course, the lower limit is not zero. We are not starting from its natural length to stretch. We start from 15 centimeters. It has already been stretched when we have 15 centimeters length. So my lower upper limit, limit, my lower limit will be the natural length subtracted from the 15 centimeters, which is 0.05. And how about my upper limit? My upper limit will also be the natural length subtracted from 0.18 meters. So that is 0.08. Be careful, okay? Be careful, because finally we will get the work is measured in joule. So that's why we should use the meters. If you write 5 to 8, then the unit is terrible. Okay, it's Newton centimeters. It's terrible, okay? Because 1 Newton meters equals 1 joule. So my lower and upper limit will be 0.05 until 0.08, okay? 0.08. Fx, 800x dx. And how you evaluate this definite integral, I'm not going to spend any time on this part. So will be 1.56 joule. But for this question, okay, for this question, so so try to understand every detail, okay, every detail. Or I think some of you made a mistake in the homework because there is a lot of tricks, okay, there is a lot of tricks. You might be easy to make a mistake, okay. So here the tricks is the lower and upper limit. I believe everyone understand how to work out the definite integral using this formula. But what is the lower and upper limit when we work on this example, stretching the spring from 15 centimeters to 18 centimeters, right? So that is this example, okay? Let's look at one more. A spring has a natural length of 20 centimeters. If a 25 Newton force is required to keep it stretched to a length of 30 centimeters, which means you stretched the spring by zero point 0.1 meters. 25 Newton is applied, is required. Then you can work out the spring constant. How much work is required to stretch it from 20 centimeters to 25 centimeters? Right? Check it carefully. Okay, check it carefully. So the natural length, mark it one by one. Okay, mark it one by one. The natural length x0, which is 0.2, right? Which is 0.2. X1, the position is 0.3 meters. What is the force required? 25 Newton, right? Equals K times my delta X. What is the delta X? The delta X is the unit. The unit beyond its natural length, right? The unit of the length. The unit beyond its natural length. The unit beyond its natural length will be delta x, right? What is delta x? 0.1, right? How you get 0.1? x1 minus x0. So here, how can I get my, so it's k times 0.1, then what is my spring constant? So my spring constant will be 250. Spring constant, k is 250, right? 250 spring constant. Then how much work is required to stretch it from 20 centimeters to 25? Lower limit, so will be this from 20 centimeters. 0.2 subtracted the natural length from 0.2, of course. Now the lower limit is 0, right? Here means from its natural length, 20 centimeters. 225 centimeters minus 0.2 natural length, so 0.05. Be careful, okay? Be careful. Then the work required. The work required. W. From 0 to 0.05. Kx. K is 250. Kx dx, right? Here means the x. Fx is, so we know Fx, the model, the force, Fx is 250x, right? Here, this x means from the zero position, to the 0.05, right? 0.05. So that is the 25 centimeters, right? So this x is not the natural length. This x is the unit beyond the natural length. Okay. So finally, what is the answer? So it will be 250 times 1/2 x squared from 0 to 0.05. So you calculate it, okay? You calculate it. Then let's take a break, okay? Let's take a break. Then we will start section 5 and try to understand those examples. We will do the quiz at the end.